Today, we want to look at flux integrals again, and we want to compare them to line integrals. Because you know me, I'm all about comparing new things to old things that we did before to see how it's similar to what we did before. We're just modifying it. In line integrals and flux integrals, we're integrating a vector field. And we know with integrating, we just need to plug a bunch of points into whatever we're integrating and then add up the results. Integration is just addition. So in the case of a line integral, the set of points we're plugging in come from a curve. So we're plugging in a one-dimensional collection of points. And so we start by parameterizing the curve. We describe every point on the curve in terms of some parameter c, where we start the curve, part of the curve we're interested in when t equals a, and end it at t equals b. The dr is a small piece of the curve in the direction of the curve. So the direction is just the derivative. And so we draw these little tangents, and we're imagining the curve to be all these little straight line segments. So with a flux integral, we want to do the same core operation, plug a bunch of stuff into the vector field. But now our collection of points comes from a surface. So that adjusts how we think of the dA, because we're making a dot product here, and we're just adding up a bunch of scalars. So the dA is going to has to indicate something about the direction of the surface and something about the magnitude of that piece of the surface. So just like the dt is the magnitude of how long this little piece is, the r prime is the direction. We need a direction and a magnitude for the dA. The magnitude of the dA is going to be the area of the piece of the surface we're looking at, and the direction of the dA will be normal to the surface. So we need a vector describing the surface. We assume the surface is just flat, because that's what we do. The other thing we do in integration, we just make everything constant. Take our curvy surface and just make it flat in these little sections. We picture the surface not curvy like a human would, but as a bunch of flat little surfaces like a computer would. So what do we need for a parameterization of a surface? It's going to be a collection of points. It's just going to be a collection of points in R3, because I have a surface. So our parameterization of the surface S, we're going to do the same thing that we did when we parameterized the curve C. We're just going to describe the points in a vector form. But since the surface is two-dimensional, we're not just going to have one input. That's a capital S, this is a lowercase s. You know what, that's a terrible idea. That's U and V. Those are the other ones, other standard ones. Instead of S and T, since I'm calling the surface S, I'm going to use U and V. So instead of having one parameter, T, because my collection of points in R3 is one-dimensional, I have two dimensions. So I'll have two parameters, U and V. Yikes. So we need two parameters to describe for the two dimensions of our surface. Any questions? All right. So the next piece that we need is we need functions for the I, j, and k vectors. So just like our r of t up here, no wonder I fit this all in one line. I forgot to write this. R of t was some, what did I think I used F1. So F1 of t I, F2 of t j. We describe all the points with three functions. We describe the x, y, and z separately. We'll do the same thing when we parameterize the surface S. So we'll have a function of u and v in the I direction, a function of u and v in the j direction, and a function of u and v in the k direction. So that is all very similar. We just generate a position vector by parameterizing all the points x, y, and z. So the surface is made up of points where with x coordinates, y coordinates, and z coordinates. So we're saying that x is f1 of u and v, y is the point x2 of u and v, and z is f3. These are all points on the surface. Any questions? All right. So we're going to do a similar thing that in the line in the flux integral that we did in the line integral. We're going to evaluate the function at the parameterization, because the parameterization is all the points, and we know the deal is that we plug in everything from the function we're integrating gets evaluated at all the points in the set over which we are integrating. Then, so that first part is going to be the same. This part is going to be an integral over, let's say, some region. I'm going to do it, I'm going to say R. The integral over R of the vector field evaluated at the parameterization. Yikes. And then we still have to deal with the dA. So R is going to be part of the parameterization. So R is going to be the region in the parameter space. R is going to be all the values of U and V. So we described the parameterization of the line integral as R of t for t between A and B. So the parameterization of the surface S is R of U and V over the region R. So R is a region in the parameter space. So R is all the values of U and V that generate the surface. Just like t is the set of real numbers that give us the curve, we have to plug in a bunch of u and v into our parameterization. So we have to describe, and since we have a surface S, we need two, and we have two parameters. The parameters are all going to be organized into some region. All right. So what we want to do is we need to write dA such that the area is going to be a little piece of the surface. Sorry, we're going to have to break up the surface into a bunch of pieces dA, where the direction of dA is normal to the surface, and the magnitude is the area of the surface. So now we need to deal with dA. We're not really parameterizing the dA. We need to write dA in terms of the parameterization. And since we're integrating over R, the dA integral needs to turn this all into a double integral du, and with a du and a dv. So it's going to have to result in a double integral du dv. Because we're integrating over a region, that's just a double integral. And so that area is going to have to show up in the du dv. But there's also going to have to be direction that is normal to the surface. So let's write down how we deal with the dA, and then decide if it makes sense. So the integral over S of f dot dA is going to be the integral over a region R from the parameterization of the vector field evaluated at the parameterization and then dA shows up like this. So this is going to be dot. We take the partial of R. We need derivatives. That's what R prime was up here. We just take derivatives. But in the line integral, everything was there was only one dimension. So we just took derivatives. F prime, F1 prime, F2 prime, F3 prime. But since F1, F2, and F3 in the parameterization of the surface are functions of two variables, we're going to end up with partial derivatives. So we'll take the partial derivative of R with respect to u cross the partial derivative of R with respect to v. And this will be du dv. So this whole piece is going to stand in for the dA, just like R prime of t dt stood in for the dr in the line integral. I usually say pause for copying, but I don't know if people are copying because this all gets posted and recorded. So I'm just going to keep going. Let's see that it makes sense. We have a cross part. We have these two derivatives. We know we needed all the derivatives. How are things changing in the u direction? How are things changing in the v direction? We need the magnitude of this dA to be the area, and that's this piece over here, du dv. We need the direction of dA to be normal to the surface, and for that we're doing a cross product. So if we have dr du cross dr dv, dr/du is how r is changing in the u direction. dr/dv is how things are changing in the v direction. And the cross product of these vectors will be normal to both of these vectors. So we've got a vector that's cross, we get our direction. Our direction is going to be normal to the surface because dr/dv and dr/du are all going to be tangent to the surface. du/dv is going to be the area, and that's what we wanted out of dA. Any questions? So all we really need to do is learn how to parameterize surfaces. Any questions? So some of you have been through a linear algebra class. Some of you will be going through a linear algebra class soon. I'm not sure where y'all came from. I know a bunch of you came from linear algebra over the summer. So we have been talking about vectors, and so that means a lot of this is related to linear algebra. And what we're trying to do is we're trying to look at, one way we think of it is we're trying to connect all these different spaces up. In linear algebra, everything connects up in a nice kind of simple fashion. So the question, does this relate to linear algebra? Yeah, because we're talking about vectors. But there are a lot more questions when we really try to get this like hooked up to linear algebra. I think that's a lot more work than we need right now. Which is an example of me bailing on a question, kind of. So other than to say like, yeah, is this related to linear algebra? Yeah. Any questions? Let's pause the video here and talk about next steps. Next steps, of course, being Thanksgiving.